So, what actually happens when the universe's tiniest building blocks smash into each other at almost the speed of light? Well, it's not just some cosmic fender bender. It's a moment of pure transformation, a moment that actually reveals the fundamental rules of reality itself. And today, we're going to zoom in and break down one of those spectacular moments.
All right, here's how we're going to tackle this. First, we'll set the stage with a collision between two quarks. Then, we'll meet the incredibly strange particle they create. After that, we'll see how physicists turn that event into cold, hard math. We'll even learn a really clever shortcut they use to make their lives easier. And finally, we'll talk about why any of this actually matters.
So let's really think about that question. In that split second of impact, what's going on? It's not chaos, it's a drama, an act of creation and decay that follows a very specific script. So let's watch that story unfold.
Okay, our story starts in a place smaller than you can possibly imagine, tinier than a single proton. And in this space, two fundamental particles are on a collision course.
So try to get this image in your head. You've got two particles. One is an up quark, one of the things that makes up the protons in your body. The other is an anti-down quark, that's its antimatter counterpart. And they are absolutely hurtling toward each other, packed with an incredible amount of energy.
Now, to figure out what happens next, physicists don't just, guess. They draw a map. It's a special kind of map for the universe called a Feynman diagram, and it shows every single step of what's about to happen.
And right at the heart of our story, the star of the show, is this guy, the W boson. Think of it as a messenger particle. It carries the weak nuclear force, which is one of the four fundamental forces that run the universe. But here's the crazy part. It's super heavy, like 80 times heavier than a proton. And it only exists for an impossibly tiny fraction of a second. It's there, and then it's gone.
Okay, this breaks down that fleeting moment perfectly. Step 1, annihilation. The quark and the anti-quark smash together and poof, they vanish, converting all of their mass into pure energy. Step 2, creation. All that energy instantly morphs into our new super heavy particle, the W plus boson, but it can't stick around. Which brings us to step 3, decay. Almost instantly, the W boson falls apart, transforming into two totally new, lighter particles. In this case, something like an electron and a nearly weightless neutrino, which then fly off into the cosmos.
Now, that little visual story is pretty cool, right? But for a physicist, that's just the beginning. The next step, the really crucial one, is to translate that picture into the precise language of mathematics. That's how you make real predictions and check if your theories match reality.
And they do this using something called the matrix element. The best way to think about it is as the complete mathematical recipe for the entire collision. Seriously, it's got everything. Terms for the quarks coming in, a term for the W boson messenger, and terms for the particles flying out. Every little detail is encoded right there in the math. Now, once you have that mathematical recipe, you can calculate a really important number, the cross-section. All that really means is the probability. It tells you how likely it is that this specific collision with this specific outcome is actually going to happen. You can think of it like the size of the target the quarks need to hit. Bigger target, more likely the event.
And that probability really depends on two main things. First, the collision energy. You've got to have enough energy in the first place to create something as massive as a W boson, E equals mc squared, right? And second, the scattering angle, basically the geometry of the whole event, the directions the new particles fly off in. Both are absolutely critical.
But here's the catch. Calculating these things with perfect precision is, and I'm not exaggerating, monstrously complex. The full equations can be a nightmare to solve. So what do? Well, if you're a physicist, you come up with a really elegant shortcut. See, the problem is that the W boson doesn't have one single perfect mass. Because of quantum weirdness, it has a tiny, tiny range of possible masses. Accounting for that whole range makes the math, well, a real headache. So you have to wonder, is there an easier way to think about this?
And the answer is yes. It's called the narrow width approximation, or NWA for short. It's a super powerful trick where physicists basically say, look, that range of possible masses for the W boson is so incredibly small, let's just pretend it's created at one single precise value. This assumption just makes the math so much simpler.
And just look at the difference it makes. On the left, you've got the full, messy mathematical term that describes that whole range of masses. It's called a Breit-Wigner distribution. But on the right is the approximation. You replace that entire complicated curve with a simple, sharp spike at one exact mass. It's what's called a delta function. It's a trade-off, for sure. You lose a tiny, tiny bit of precision, but you gain a huge amount of simplicity. But here's the really crucial point. This isn't just some wild guess. Physicists know exactly when this shortcut is valid and when it isn't. As the source material points out, it works perfectly fine as long as our detectors and measurement tools aren't sensitive enough to even notice that tiny natural fuzziness in the W boson's mass. It's a practical tool for a practical world.
So why? Why go through all this trouble? Drawing diagrams, writing down complex equations, finding clever shortcuts. What's the point? Well, because it's not just about one little collision. It's about putting our most fundamental theory of the entire universe to the test.
So let's just quickly recap our journey here. We saw that a particle collision isn't just random. It follows a script that we can map out. We learned that this map can be turned into a mathematical recipe that lets us predict how likely it is to happen. And we found out that to deal with that insane math, physicists have clever tools like the narrow-width approximation. Every single one of these steps is how we ask the universe a question. Hey, is our theory about you, the standard model, actually correct? And so far, the universe keeps saying yes.
And that kind of leaves us with one final thought to chew on. At its deepest level, the universe seems to follow these incredibly elegant, sometimes simple rules that are hidden inside all this complexity. This one approximation is just a tiny example. It makes you wonder, what other beautiful shortcuts, what other deep truths are still out there just waiting for us to find them?